Hello, welcome to the Baillie Gifford stage and to this event, which is organised in partnership with British Pugwash. We first started working with them in 2005, and the Weapons of Mass Destruction Awareness programme run that was part of Joseph Rotblat's great campaigning zeal. Our guest today is an extraordinary man, a teacher of extraordinary distinction. He teaches at the University of Surrey. He is a broadcaster, possibly the finest interviewer on Radio 4, where he presents The Life Scientific. And he's written 12 books of popular science of great acclaim and a novel, Sunfall. He's here to talk about his new book, The World According to Physics. Please give a very warm welcome to Jim Al-Khalili.
Thank you very much indeed, Peter. Well, it's an absolute pleasure to be here. Well, not there, but here. I was explaining to Peter earlier that it's quite remarkable to be doing these sorts of talks and festivals online. Here I am in my home in Southsea in Hampshire. You can't see, but I'm wearing shorts and flip-flops, because it's a lovely, lovely day. But I do hope you enjoy this lecture. Before I start talking about the subject about my new book and the subject of my lecture, I wanted to say just a few words about Pugwash and indeed Joseph Rotblat. As Peter mentioned in the introduction, British Pugwash are sponsoring this particular event. The Pugwash conferences on science and world affairs is an international organization. It goes back to the mid-1950s. It brings together academics, scholars, world leaders to discuss ways forward to reducing the dangers of armed conflict and look for solutions to global security threats. Joseph Rotblat was a nuclear physicist. He was one of the founders of the Pugwash conferences together with Bertrand Russell. I wanted to say just a few things about him because, as I mentioned, he's a nuclear physicist, as of course am I. I met Joseph only once, about 23 years ago. This was at the Royal Society in London at their summer exhibition and soiree. Joseph was born. He was in his 80s by this time when I met him in 1997. And on that evening, I was presenting some of my research in nuclear physics. So I had a display showing the atomic nucleus made up of red and blue ping pong balls to designate the protons and neutrons, the constituents of the nucleus. And as I'd been accustomed to explaining my research to the various guests on this evening, various dignitaries, many scientists, but of course, not many of them experts in nuclear physics, unbeknownst to me, Joseph Rotblat came up to our stand and asked me what it was about. So I said, well, okay, let me start by asking you, how much do you know about nuclear physics? Thinking he'd say nothing. He said, young man, I've probably forgotten more nuclear physics than you know. So that's when I looked at his name badge and saw it was Joseph Rotblat, the great nuclear physicist. He was born in 1908. He died in 2005 when the series of lectures actually began at Hay. He had studied nuclear fission, the process by which a heavy nucleus splits into two, releasing energy. That's what powers nuclear power stations. He worked with Ernest Rutherford. He worked with James Chadwick, the discoverer of the neutron back in the early 1930s. Joseph's wife, Tola, he was from Poland, of course, Polish Jew. He had escaped Poland, but he was unsuccessful in getting his wife Tola out of Poland, and sadly she died in the Holocaust at Belzec. Naturally, this stayed with him for the rest of his life, and he never remarried. He worked on the Manhattan Project in Los Alamos, and when in 1944 it became clear that Germany weren't going to be successful in building their own atom bomb, he asked to leave the project. He had huge, serious reservations from that time. Of course, then he was, the authorities tried to frame him as a Soviet spy. He left the US, he came to the UK and settled in Liverpool, the University of Liverpool, and the nuclear physics group there. He then went on for the rest of his career, determined to use nuclear physics for peaceful means, for example, in nuclear medicine. He also believed that scientists had a moral responsibility in the same way that medics have their Hippocratic oath. He wanted a Hippocratic oath for scientists as well. His research certainly contributed in the 1963 to the partial nuclear treaties ban. He was the Secretary General of the Pugwash conferences ever since its founding in 1957 all the way to 1973. Joseph Rotblat and the Pugwash conferences jointly won the Nobel Peace Prize back in 1995 for efforts to diminish the part played by nuclear arms in international affairs and, in the longer run, to eliminate such arms. So it's a great pleasure to be the latest speaker in this Hay series of lectures to commemorate Pugwash and indeed Joseph Rotblat himself. Right, well, let me say something then about, well, something, this is everything. This is what I'm going to be talking about for the next half an hour or more, about my new book. It's called The World According to Physics. What I try to do in this book, and what I will try to do in this talk, is to get across the excitement of cutting-edge physics today. In a sense, and I say this in the introduction to the book, it's my ode to physics. It's really trying to share with readers my love affair with the subject that I've had ever since I was a teenager. So over 4 decades ago. And I'm still as fascinated, still as excited, still as mystified by so many aspects of physics now as I was when I first fell in love with the subject. See, physics, and probably more so than any of the other sciences, because it really addresses the deepest questions about the nature of reality, the meaning of the physical universe and our place in it. And it's not just another way of learning about the truth of the deeper truth of the way things are, the nature of reality. I would argue it's the only way. No ideology, no religion, no philosophy, no amount of metaphysical debate can reach or attempt to get as close as possible to that ultimate truth of the nature of reality in the way that physics does. So, as you can tell, I'm pretty adamant about this. I don't want to proselytize too much. I assume probably to a large extent I'm preaching to the converted, which is good, using metaphors from religion. So for me, what is, I guess, exciting, because I'm a theoretical physicist rather than an experimentalist. So I don't work in a lab. I don't conduct experiments. I don't take measurements and collect data. I try and use mathematics to understand the nature of the universe. And it's always been remarkable to me that mathematics is the language that nature speaks. We're not inventing mathematics and somehow that reflects what happens in the real world. The real world out there uses mathematics, that it is designed mathematically. And I find that remarkable. And when I talk about physics giving us a deeper truth in a way that no other belief system can, the simplest example I can think of is this. If you drop a ball from a height of 5 meters, then the laws of physics tell us that that ball will hit the ground after 1 second. Now, by ground, I mean on Earth. I'm talking about Earth's gravity. But drop a ball from 5 meters, it hits the ground after 1 second. Not 2 seconds, not half a second, but 1 second. And no amount of meditation or thinking or philosophizing will give you that number of 1 second. Physics does. A simple mathematical formula first developed by Galileo. And we see time and time again, we're uncovering truths about the universe by developing our mathematical theories. Now, this book, The World According to Physics, is, in a sense, if we think about all physics knowledge as an island, and there are many popular science books that explain how we came to understand and explore this island. Beyond its shores is the ocean of the unknown, the yet to be understood, the yet to be discovered. And it's a big ocean, and we don't know how far out it extends. This book isn't an exploration of the island, it's a trip around the shoreline, investigating what we currently know at the cutting edge of physics at the end of the second decade, beginning of the third decade of the 21st century. And we will dip our feet in the water a bit and try and explore a little bit of what we have yet to understand. So if we look back to the end of the 20th century, in fact, this is a paper from Stephen Hawking from 1981, in which he asked whether physics is coming to an end. In fact, he says, I don't know if you can, yes, you can probably, I've enlarged that first paragraph for you. In this article, I want to discuss the possibility that the goal of theoretical physics might be achieved in the not too distant future, say by the end of the century. By this, I mean that we might have a complete, consistent, and unified theory of the physical interactions which would describe all possible observations. What Stephen Hawking is saying here is that we're getting close to a theory of everything, a single theory that encompasses and explains all physical phenomena. And I say physical phenomena, the theory of everything isn't going to explain economics or psychology, for example, but the physical universe. Stephen Hawking was wrong. We are in fact further away from this theory of everything now, we think, than we thought we were towards the end of the 20th century. And in fact, that's not the first time physicists felt all they had to do was dot some I's and cross some T's, because at the end of the 19th century, physicists also thought that we'd pretty much discovered all we were going to discover about the world. You know, we had Newton's laws of motion, we had his law of gravity, we had Maxwell's theory of electromagnetism describing the nature of light, electric and magnetic fields. We had thermodynamics and the nature of heat transfer. What else is there? And then you hit that last decade of the 19th century and we discover the electron. We discover X-rays, radioactivity. No one was expecting this. And then the beginning of the 20th century, we have Max Planck coming up with the revolution in quantum theory, saying that energy down at the tiniest scale isn't continuous, but comes in lumps, discrete quanta. Einstein gives us his two theories of relativity. And suddenly we realize what we thought we knew about the universe was just a crude approximation. And there was so much more we needed to discover. Are we, therefore, in a similar position today? Maybe, maybe not. But I want to talk you through what we know and what we don't know at the moment. So if we think back to, say, just in the last decade, and the advances that have been made, the discoveries that have been made. 2012, of course, was the discovery of the Higgs boson at the Large Hadron Collider, and there's a picture of Peter Higgs, after whom the particle is named. And then just a few years later, in 2016, was the confirmation of the existence of gravitational waves, ripples through space itself, formed from a cataclysmic event very far off in a distant galaxy. In this first case, it was the collision of two black holes. So incredible was the energy produced in that collision that waves through space itself was rippling outwards, a bit like dropping a stone in the middle of a pond and the ripples then spread out radially to the edges of the pond. Well, here, the edges of the pond are Earth and instruments, an experimental facility called LIGO in America, which detected these faint ripples. The event took place over 1 billion years ago, over 1 billion light years away, and yet we detected it. How wonderful these two incredible discoveries were in physics, and of course they made headline news around the world. But neither of them was unexpected. In fact, it would have been more of a surprise had we not discovered the Higgs boson at the Large Hadron Collider. It'd been predicted, after all, half a century earlier by Peter Higgs. Gravitational waves were predicted by Einstein to exist 100 years ago. In fact, exactly 100 years before they were discovered. So in a sense, these were box-ticking exercises. Yep, we knew there was the Higgs out there, we found it. Yep, gravitational waves, finally detected them. They weren't surprising. So they didn't really lead to a revolution in physics or a change in our theories. They confirmed our theories in a sense. Now, contrary to popular belief, physicists don't want theories to be confirmed. We want theories to be destroyed. We want to come up with a new idea. We want the revolution. We want the Nobel Prizes. We want to go back to the drawing board. After all, if we have all the answers, then, well, it's not so exciting, is it? There has, however, been one discovery, certainly during my career as a physicist, that was truly unexpected. And that happened back in 1998, and it's the discovery of dark energy. So this is my depiction of dark energy. This wonderful picture was drawn by an artist by the name of Jeff Cummins, who helped me produce a little Ladybird book on gravity. You remember the Ladybird book formats? You'd have one page of text and one page with a beautiful illustration. Well, I've stolen, with Jeff's permission, I should say, some of these pictures to show in this lecture. So, dark energy. You may have heard of it as some mysterious thing that these boffin physicists are coming up with. What happened though in 1998? Well, astronomers were looking at distant galaxies. We've known since the 1920s that the universe is expanding. It's getting bigger. It's not that objects are moving through space away from each other. It's that the space in between them is stretching. All galaxies are staying where they are in their local vicinity within space, but the space between the clusters of galaxies is stretching. And it was always thought that if the universe started in a Big Bang, a time when all matter and energy was condensed together in a very high density, high temperature lump, then as it expands, gravity should gradually be putting the brakes on that expansion. After all, gravity is an attractive force. It's pulling things together. So all the stuff of the universe should be slowing down the expansion. And we didn't know whether it was slowing it down enough to stop it expanding and cause it to then collapse in on itself like a stretched spring that then, if you let go, collapses in on itself. Or maybe it was expanding like blue tack, when if you stop pulling it, it doesn't stretch, goes back to what it is. It stays at the size that you've left it. In 1998, it was discovered that, in fact, the universe's expansion is speeding up. It's not slowing down. There's some mysterious force of anti-gravity, in a sense, that's pushing stuff apart and that is winning the battle against the attraction of gravity, acting in the opposite direction. And we called it, for want of a better term, dark energy. And we're still trying to understand exactly what dark energy is. Of course, there's still a lot to understand. So dark energy, in a sense, is already dipping our feet in the water beyond the shoreline of what is known. There are other mysteries out there. There's the similarly named dark matter, which has nothing to do with dark energy. Dark matter should have been better named invisible matter. It's out there in space. It holds galaxies together. We just can't see it. It has gravity. We know it's there, but we don't know what it's made of because we can't see it. So lots of experiments are taking place and have been for many years now to try and understand the nature, the composition, the ingredients of dark matter. Again, a mystery out there in the ocean of the unknown. There are other questions like, was there something before the Big Bang? Or was it the beginning of space and time? Is the universe infinite? Does it go on forever? Or is it finite? We understand that just after the Big Bang, equal amounts of matter and antimatter would have been created. And yet today, all we see around us is mostly matter. So where do all the antimatter go? Well, these are things we haven't understood. But physicists feel very confident that we will one day understand them. Now, this isn't arrogance. This is because past experience has taught us that phenomena that we haven't understood can gradually be incorporated within our understanding as we develop better, grander theories that encompass more and more of nature's forces, of the phenomena and mechanisms that we see around us in the universe. Then this is a journey that we call unification. So I want to show you in the next slide how we've unified various areas of physics. I should warn you, it's a very busy slide in the sense there's lots of words and the fonts are very small. I hope you have the resolution on your screens as you watch this to be able to decipher it. Oh, in fact, you really can't, because it's actually at right angles to what it should be. Okay, so this I don't know if the tech guys, no, you probably can't do it as it's happening. Not to worry. So I'm now making use of the technology to see whether I can talk to the technicians here. Look, kill this slide. Just come to my lovely face, and I will just talk you through it. It was a busy slide. It really wasn't that interesting anyway. If we think about the earliest example of unifying physical phenomena that had previously thought to have been unconnected, we go back to Isaac Newton. It was Newton supposedly sitting under the apple tree on his mother's farm during the plague, and presumably under lockdown, one would say, and contemplating the nature of the forces of the universe. And he realized that the attractive force that pulls the apple down to the ground, the force that we now call gravity, is the same force that keeps the moon in orbit around the Earth and the Earth in orbit around the sun. Now, today we say, yeah, well, it's just gravity, right? The moon's caught in Earth's gravitational field and it's orbiting the Earth. But that wasn't obvious back before Newton. There were forces that took place here on Earth. Objects had a tendency to fall to the ground. And then there were the forces in the heavens that were regarded as being quite different. Newton said, no, it's the same physical phenomenon. It's the force of gravity. And he comes up with his theory of gravity. So that's the first example of unification. Thereafter, we think about in the 19th century, people like Michael Faraday at the Royal Institution in London carrying out experiments with electric currents and magnets, and realizing there's a connection between electricity and magnetism. the Scottish physicist James Clerk Maxwell develops a beautiful mathematical theory showing that electric forces and magnetic forces are one and the same thing. They're part of a general force called the electromagnetic force. And in fact, within his theory, he also shows that light itself is nothing but oscillations through the electromagnetic field. It's oscillating electric and magnetic fields traveling through empty space. There's another of unification. Two things that were seen to be quite different, the magnetic attraction and electric currents, they're the same thing. Today we take it for granted. After all, that's how motors work, how a dynamo works, creating electricity from motion in a magnetic field. By the 20th century, the ideas of unification really pick up pace. Einstein shows that time and space should be unified into four-dimensional space-time, and he develops his special theory of relativity in 1905. He then unifies his special theory of relativity, in a sense, with Newton's gravity, and comes up with a new picture of the force of gravity. Einstein says gravity isn't even a force at all. It's the shape of space-time. From his general theory of relativity in 1915 emerges a whole new area of science cosmology, scientific cosmology, describing the nature of the whole universe. At the same time that Einstein is looking outwards at the larger scale, physicists are also looking inwards at the tinier scales. At the beginning of the 20th century, people like Max Planck, Albert Einstein, Niels Bohr are developing quantum theory, the theory that describes the world of the very small. And by the 20th century, they had really completed, by the late 1920s, they had completed their new theory, which we now call quantum mechanics, describing the behavior of atoms and the particles that make up atoms. Quantum mechanics, therefore, was then used to unify other forces of nature. Quantum mechanics describes the electromagnetic force. It describes the nature of the forces within atomic nuclei. We developed theories that combined quantum mechanics with Einstein's special theory of relativity. So, and describing the electromagnetic force in terms of quantum mechanics. Theories called quantum electrodynamics. It culminated, and it has culminated by the mid to late 20th century, with something called the Standard Model of particle physics. So this is a theory that brings together our current understanding of the quantum world, the world of the very small. It includes within its description three of the four forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force, two forces that act within the confines of an atomic nucleus. The one force that the Standard Model of particle physics doesn't explain is gravity. But as we've heard, gravity, in a sense, is not a force at all. It's geometry. It's the shape of space-time in a way that, I'm not going to be able to explain in just a few minutes. But I want to say this, that the quest for unification has continued. Physicists now regard, and this is what Stephen Hawking was talking about in that paper when he said, is the end of physics in sight? We're looking for a theory that combines Einstein's theory, general theory of relativity, the Einstein's theory of gravity, space and time, and the very large scale, together with quantum mechanics, or the Standard Model of particle physics. And we're not there yet. We have candidate theories that might be the correct theories of what we call quantum gravity, but we're not there yet. Here's another picture from the Ladybird book, artwork by Jeff Cummins, showing a struggle between the two of the leading candidates for theory of everything, a theory of quantum gravity, depicted as an arm wrestle between two superheroes. So on one side, you have string theory, developed in the mid-1980s, which unifies all the forces of nature mathematically, but we still don't have any experimental evidence that it's the correct theory. We've been looking for particles at the Large Hadron Collider called supersymmetric particles that really would lend experimental support and evidence to suggest that string theory is correct. It's beautiful mathematically, but it's a theory that is very hard to visualize physically, because it says our reality, our universe is in fact not just 4 dimensions, 3 of space-time, but we live in a universe of dimensions. The other dimensions being curled up very small, far smaller than we can currently probe and measure experimentally at particle accelerators. On the other side, you have the other superhero represents another rival theory called loop quantum gravity. Now, loop quantum gravity isn't in a sense a theory of everything. It's a theory that tries to quantize space-time. That is, bring space-time into the remit, into the arena of quantum mechanics. And again, there is still yet no evidence that loop quantum gravity is correct, and we're still looking for, maybe neither of them are correct, but this is what makes this fundamental physics so exciting. We still don't know how far we've got to go before we reach a theory of everything. So just I want to sort of quickly go through a few ideas and show you just how far we are from understanding some of these concepts. Even something simple like, what is space? Right? Space is where we exist in, right? Is this the place that things happen? But what is space? What is time? Maybe we don't know yet what they really are. An example is this: does the space inside an empty box exist in reality, or does it only exist because it's surrounded by the walls of the box? If you have a vacuum, emptiness within the box, and you remove the walls, does the space even have any independent existence or meaning or reality? Well, Isaac Newton thought that yes, space does have, it does exist independently of the stuff in it, the matter in it. It's the canvas on which, reality paints its pictures. It's the place, it's the stage where events take place. Without space, nothing could happen. So Newton says there has to be space, and then it can have matter in it. Other thinkers like Aristotle and Descartes said that no, space doesn't exist unless there's something in it. It doesn't have an independent reality. Well, our current best idea of the nature of space really is down to Einstein, and that would say that in some sense Newton is correct, that space is real. It's a thing. It's stuff. But it's more than just the gap between 2 points, 2 places, 2 objects. However, Newton wasn't right in thinking that space has an independent reality, that it can exist apart from matter and energy, without matter and energy. Einstein says that matter and energy create a gravitational field, and that gravitational field is space-time. So without matter and energy, there would be no space-time. In fact, Einstein's equation of general relativity, an equation, if you think, I'm not going to show you the equation, don't worry, but an equation has an equal sign. And on one side of Einstein's, what's called the field equation, is space and time, and the geometry, the shape of space and time. And on the other side is stuff, matter and energy. And one requires the other for there to be a universe. And so Einstein published a book in 1916, and rather than having multiple editions of the book in which he changed things and modified them, would would do was add appendices to the book. And the very last one he added in 1954, a year before he died. And in it contained some of the most profound and beautiful and deep ideas about the nature of reality. So I'll just have this one quote I read to you. Space-time does not claim existence on its own, but only as a structural quality of the gravitational field. It's a deep and profound idea about the nature of what we regard as common sense. Space is 3D space. It's where stuff is. The universe occupies space, and you put matter in the universe. But Einstein says you can't have empty space without matter. It doesn't have any meaning. And then, what if we zoom down onto the tiniest scales of space and time? Does it remain continuous? Does it remain, can you zoom deeper and deeper and deeper, and does it stay smooth? The other theory of physics, quantum mechanics, tells us essentially that space and time should, at some tiny, tiny scale, become lumpy, will start to lose their meaning. Now, quantum mechanics, which is the theory that I've spent my career working with and studying, is famously difficult, right? Quantum mechanics, okay, well that'll give you a headache. Yeah, it'll give you a headache. It still gives me a headache, but that doesn't mean I love it any less. Quantum mechanics is the most powerful, the most beautiful, the most important theory in all of science. See, that's it. And I know there are many biologists, friends of mine, will say, don't be silly, Darwin's theory of natural selection is more important. Anyway, I'm a physicist, I'm biased. But quantum mechanics, without it, I wouldn't be giving you this talk, right? Because modern electronics only works thanks to quantum mechanics. But at its heart, quantum mechanics is mysterious. It's counterintuitive. In fact, it's the only important theory in all of science that has got away with not having a proper single explanation of the mathematics. Now, a physical theory, a mathematical theory, may be a set of beautiful equations, but that's meaningless unless you add the narrative to those equations, the meaning. What do the symbols mean? How do they connect to the real world? Quantum mechanics has at least half a dozen ways of explaining what the mathematics means, and we're still arguing about it. So here again is something else that is out there yet to be resolved. Many physicists have given up trying. Look, quantum mechanics works, it's powerful, the mathematics makes predictions, it's allowed us to understand the nature of matter down at the tiniest scales. If you're going to worry about what it all means, cats in boxes being dead and alive at the same time, all that business, go and do philosophy. That's not my attitude. My view is that as a physicist, I want to know how the world is, more than what I can say about it, or what my equations say about it. And this is a different philosophical approach. Let me show you quotes. These are from three leading scientists, physicists. First of all, Niels Bohr. He says, it's wrong to think that the task of physics is to find out how nature is. Physics only concerns with what we can find out about nature. We can make predictions that we then go and do an experiment, and sure enough, the prediction is borne out. The theory is correct. It allows us to understand the world, but it's not telling us how the world actually is. On the other hand, people like Einstein and John Bell, the famous Irish physicist, so John Bell says, to restrict quantum mechanics to be exclusively about piddling laboratory operations is to betray the great enterprise. And Einstein says the job of physical theories is to approximate as closely as possible to the truth of physical reality. Now, philosophically, I'm a physical realist, I would say. I believe there's an objective reality out there. So I would side with Einstein on this. And it's an unresolved issue. I'm not saying I'm right. I don't know. That's the beauty that a scientist can say, I don't know. We'd like to find out. But my view is that there is an ultimate truth out there, the way nature is, the way the universe behaves. And it's the job of physicists to try and find out what that reality is. How far away are we? I want to bring this to a close in just a few minutes. So let me just say one or two things. First of all, about the nature of time. Again, Einstein's theory of relativity is our best theory of the nature of time, we would argue. But here are what I call the three pillars of physics. General relativity, the theory of the very large; quantum mechanics, the theory of the very small; and thermodynamics, the theory of the in-between, the stuff that we see around us in the everyday world. Each of them gives us a different definition of the meaning of time. General relativity says time is a dimension. It's the fourth dimension of space-time. It's a dimension that can be stretched, it can be bent, it can be warped by gravity. Quantum mechanics says, no, time is more boring than that. Time is just a number. You plug in, if you've got your equations of quantum mechanics to describe, say, what an electron is doing at any given moment, you crank the handle and you can work out what it might be doing at another time in the future. You could also crank the handle backwards and work out what it was doing in the past. Time is reversing quantum mechanics. And then you come to thermodynamics, the theory of heat, the theory of energy, and how how matter can use energy to make things happen. It's the theory of change. And it says time isn't a dimension or a number. It's an arrow pointing from the past to the future. You can't reverse. Things only go one way. A broken egg cannot be reconstituted. We get older, we don't get younger. We remember the past, we look to the future, not the other way around. So it cannot be reversed. So here are our three most fundamental theories in all of physics, and each of them gives a different definition of something as basic as what is time. There are other issues that we have yet to figure out. For example, one popular one is, was the Big Bang the beginning of everything? Was anything before the Big Bang? Well, Stephen Hawking famously came up with a proposal that suggested as we get closer and closer to the Big Bang, time itself loses its meaning. It becomes more like a direction in space. And so there isn't a moment, what we call a singularity at the Big Bang. It's a bit like saying, walk south to the South Pole, and when you get there, carry on going south. Of course, meaningless. You can't. Any step you take from the South Pole takes you back north again. So that suggests that it's meaningless to say what was before the Big Bang, because there was no time to embed the word before in. Okay, that was the beginning of time itself. And yet there are other ideas that suggest maybe there was something before the Big Bang. There's an idea called inflation, which suggests that just after the Big Bang, the universe started to expand very, very rapidly for good reasons, but it's something we still have to confirm experimentally. Now there's an idea that maybe our Big Bang happened after inflation, that there's inflation taking place in what's called the multiverse, and our universe is just a bubble in the multiverse. We had our own Big Bang, and there were other universes having their own Big Bangs, and multiple parallel universes like bubbles. Here's another picture from Jeff Cummins, creating a multiverse. You might not be surprised to know that I quite like this picture, me creating the universe. And so these are ideas that we have yet to understand. These are ideas that we are still trying to figure out, I'd like to think we will get an answer to them in the coming decades, but we don't know. It may be 100 years before we find answers to these questions. We still have yet to figure it out. I think that's probably a good place to stop. In the book, I leave it hanging as to whether we need another Einstein come along and fix things, or whether we're getting close to theory of everything, or whether it may take another 100 years, or maybe even we require the help from AI to solve some of these problems in physics. But who knows? That's what makes it so fascinating and wonderful. Thank you very much. Are you muted, Peter?
I'm going to rattle through some questions now. Thank you for that. It was wonderful. Jemima asks, if you could investigate any theory without constraints of time, money, or even feasibility, what would you want to explore?
I think I'd want to find the correct interpretation of quantum mechanics. There are ideas that, there's called the many worlds interpretation, there are parallel realities. There's the idea that, signals could be sent back in time. There's the idea that all of the universe is interconnected by some quantum field. All these wacky and crazy ideas explaining quantum mechanics, each has its own supporters, who promote it, almost like, religions. But the universe doesn't care the arguments that we have in different interpretations. Either there are parallel universes or there aren't. Either there's a quantum field or there isn't. So I would like to know what is the correct explanation of how the quantum trickery takes place.
Similar question coming from Tony, who asks, what has been the most surprising discovery in physics of the last 20 years, and what has been the most important discovery of the last 20 years?
Well, so by 20 years, that means it leaves us out dark energy in 1998, which was 22 years ago. Certainly dark energy, as I mentioned in my lecture, was the most unexpected discovery. I think more recently, I would say the most unexpected or surprising thing is that we haven't discovered anything more at the Large Hadron Collider. You see, once the Higgs boson was discovered, it was assumed that we were going to discover new particles, maybe prove an idea called supersymmetry, that we would, other mysteries would be resolved. What is surprising is that we haven't. It's frustrating that we haven't yet found anything more. It's surprising that we haven't made the progress we'd like to make, to the extent now that many physicists are almost becoming impatient with those working at the frontiers of physics on string theory or ideas in cosmology and inflation, that we haven't been able to find the experimental test to verify some of these ideas yet.
John asks, how do particles and forces interact at a distance? For example, how does an electron in an atomic orbital know about another electron in the same orbital? And how does it know to take a different spin? How does a magnet in the proximity of another magnet?
Well, I think if you come to something, we're talking about sort of classical electromagnetism, like two magnets, they know about each other because they are existing in each other's magnetic fields. The magnetic field is stretched through space surrounding the magnets. This is what the lines of the field are what you see with the iron filings. And so they know about each other's existence, but only because of the influence of the other one's magnetic field where they are. So if one of those magnets were to suddenly disappear, the other magnet wouldn't know about it until the information traveled through, the distance between them, because the nature of the magnetic field is that it's electromagnetic waves can only travel at, by definition, the speed of light, because that's what light is. So they know about each other not by at distance, but by being immersed in each other's magnetic field. Now, the other question, whether two electrons in the same orbital know about each other, well, if these are quantum entangled electrons, then that's a whole nother ball game. How do distant quantum entangled particles know about each other? Despite what any physicist tells you, this is not something we have actually completely understood. How can something over here, you make a measurement and instantaneously something over there behaves in a different way, somehow faster than the speed of light? There are mathematical ways that we can wriggle out of it, but ultimately that is still actually a mystery, the nature of quantum entanglement.
Okay, Noel asks, we have some idea regarding the lifetime of stars like the Sun. How long does a spiral galaxy like way go on for? Does it all end up in the black hole at the center of the galaxy?
No, well, I guess ultimately a spiral galaxy, so stars have a lifetime, that's right. They will, once they die out, depending on their size, their mass, they'll turn into different things. Our sun is not going to form a black hole by itself. It's not big enough. It'll form a white dwarf star. Much larger stars, when they collapse at the end of their lives, they will explode as supernovae and leave black holes behind. We've seen already from gravitational waves being detected that black holes can merge, coalesce, and create a larger black hole. We know that galaxies like the Milky Way have a supermassive black hole at the center, and that supermassive black hole will eat stars for breakfast. Any stars that get close enough to it get sucked in. But for example, our solar system, long after the sun has died, billions of years from now, we're too far away from that black hole to be pulled in. So all the time the galaxy is revolving and rotating, we will be too far to be formed in. So eventually, matter will start to clump together, but it doesn't necessarily mean we'll all end up in one single black hole at the middle of the galaxy.
Okay, this is a slightly different question. Jen asks, my son is currently studying A-level physics. He finds he understands the concepts, but has to work very hard at the maths. Did physics and the associated maths always come naturally to you, or were there areas you really struggled with as a student? And how did you overcome them if this was the case?
I mean, I have to say that the part of the reason why I enjoyed physics was because it was mathematical, the bits that I liked. For me, physics is problem solving and common sense, puzzle solving and common sense. But of course, physics, like all areas of science, is very broad, and not everyone enjoys doing the maths. I have many absolutely brilliant colleagues who conceptualize and see the world clearly and design experiments that test aspects of nature, and yet hate doing algebra, hate solving equations. So, the theorists enjoy the maths, but that's not the only way you can do physics. I didn't like, for example, remembering stuff. That's why I guess I didn't move towards chemistry or biology. For me, it wasn't about remembering facts or names of things. I wanted to be able to work it out logically, step by step. You can do that with the maths, but you don't have to. Unfortunately, doing A-level physics, there are a few formulae that you have to remember. You have to be able to plug in some numbers to get answers out, but you don't have to. If you want to carry on doing physics the rest of your career, it doesn't have to be all maths.
Julie asks, is there a way to explain what happens to time at a very, very large or at a very tiny subatomic scale? Is time circular, or does it become fuzzy, or is it something else that we can't describe from the perspective of our daily life at human scale?
I think that's a good question. It's a good point. Certainly down at the tiniest scales, we think something down at what's called the Planck scale, the shortest intervals of time that make any sense at all, corresponding to the shortest distances in space that make any sense at all. We think that time probably becomes granular, it becomes lumpy, it loses its meaning. But we don't know for sure. And certainly on the larger scales, time is described by Einstein's general theory of relativity, where it's smooth, where it has to be unified with space, but also where it's affected by gravity in a way that, in our everyday lives, we don't see. Gravity can slow time down, for example. Gravity doesn't just make apples drop to the ground or keep the moon in orbit around the Earth. It slows time itself down. And we know this to be true. This is not just a theory. We know it to be true because GPS satellites operate in that way. We have to deliberately slow the clocks down on board the satellite computers because the satellites are feeling weaker gravity far from the Earth. And so time runs a little bit faster up there than it does down on Earth. So yeah, there are different ways of explaining the nature of time. And that's what I think is one of the big problems in physics at the moment. We haven't got this unified picture of what time is on all possible scales.
Okay, big one from Neil. Why do some physicists believe in the notion of God?
Well, why does anyone believe in the existence of a higher power? I mean, for many people, having a faith is not something that you can explain rationally or that fits into a scientific formula. It's fair to say that most of the scientists I know are not religious, don't believe in a divine creator or some supernatural intelligence. But then I also know some brilliant physicists out there for whom their faith is very important. And I think the point is that it doesn't necessarily have to conflict. They don't have to rub up against each other, or you can avoid it. Now, I'm not religious myself, and I'd like to understand the nature of the universe without intervention from something else. Because for me, if I say, well, how did that happen? Well, because some supernatural creator, divine creator, God created like that. My next question is then, what created God? Or explain God. And for somehow that sort of stops the argument. But I'm not naive enough to think that there aren't very powerful, intelligent arguments in support of the existence of a divine creator from people for whom that is important. That's why I don't get into, despite being an atheist and a humanist myself, I don't get into arguments about religion, because these are senseless arguments that no one's going to win.
There's quite a groundswell of opinion here asking whether or not you can, or indeed whether or not you will, play the ukulele that's just behind you on your shelf.
No, I'm not. In fact, one of my lockdown projects. I'm putting it down now. One of my lockdown projects was that I would learn. I'm relatively musical in that I can pick up an instrument and learn it very quickly. But of course, for those who play the ukulele, know it's tuned very differently from a guitar, and so all the chords that are familiar playing guitar are different for a ukulele. I've started, but maybe next year I might give you a rendition if I get the time.
Yeah. Good book. Last question, I'm afraid, because we're running out of time, and it's from Jerry, who asks, which one, and if you like, I'll give you three, which three scientists from the past would you most like to interview on the Life Scientific?
Okay, this should be easy. Einstein, of course. Niels Bohr, the father of quantum mechanics, who was so brilliant. I mean, I don't agree with all his philosophical views, but he's still absolutely one of my heroes. And then, of course, it would have to be, I don't know, Richard Feynman, I guess. I know I've got three men, and I know that certainly Einstein and Feynman were not the most, the ideal role models in terms of their characters, but in terms of their physics, I have to say their contribution to our understanding, I'd have to say Einstein, Bohr, and Feynman.
Jim, thank you very much for being with us for this hour. It's been absolutely thrilling. Everybody out there, buy this book.
Thank you very much, and I hope to be back in person next year. Thank you.